Optimization is a topic that we cover in math a lot, especially in upper level math, because we always want to know when we're designing something or setting something up, what are the best and kind of worst case scenarios it could be. So we've already looked at optimization back in probably Calc 1, first semester calculus if you've seen it before. But we're going to take just another approach using some new methods that we have. Today we're going to talk about something called Lagrange multipliers. Let's take a look at something where this might apply to, and you can kind of see where this method came from. Let's say we have an ellipse. I don't know, let's say it's, and I don't know, so we got this ellipse shape here. If I said, what is the biggest rectangle that we could fit inside here? So I'm just going to draw a rectangle real quick, some rectangle inside of here. And I said, what's the rectangle with the largest area? When I say biggest, what's the rectangle with the largest area that we can actually fit inside this ellipse? Well, the way that I drew this, the equation for this ellipse is what? X squared over 9 plus y squared over 16 is equal to 1. So that's the constraint. Remember with our optimization problems, a lot of times we had a constraint, right? That's what's constraining the size of our rectangle. So what are we trying to optimize? Well, we're trying to optimize the area of this rectangle. So our area here, well, since we don't know the exact size of this, you can think about this as just pick one corner that has an x and y coordinate. So the length of this side, well, if that's x, that side would be 2 x's. And the height, if that's y, the other way would also be a y, so that would be 2y. So the area of this would be 4xy. Now, one way that we could approach this problem is we could guess. We could pick up certain values for x and y and see which one gave us the maximum value. Well, that's one way to do it, and that's kind of what we're going to do. Let's say that we randomly picked values for the area, and I'd say I picked, I don't know, 7. Well, if you were to graph this, you would get y is equal to 7 over 4x. Well, that's a hyperbola, and it would look something like this. There would be a curve over here and a curve down here to match it. Well, you would keep picking values for x and y until the curve that you get, the area exactly matches the ellipse, right? Because that's the constraint. So we could keep picking values when we would want the one that just is exactly, say, tangent to the curve right there. Well, if it's tangent to the curve right there, that means they're basically the exact same function at that spot. Now, also means that they would have the same normal vector to that curve there, right? So you'd have one normal vector, let's say that that's the normal vector for this curve, and then the ellipse would also have another normal vector right there, and it would point in the same direction. So let's say that that was the normal vector for the ellipse, and that was the normal vector for our rectangle. Well, what do we notice about these two normals? Well, of course they point in the same direction, but they could be different lengths. That just means that one normal vector is a constant multiple of another one. And we've seen in the past, to find these normal vectors, all we have to do is find the gradient once we move everything to one side. So here's what Lagrange had to say about it. If you want to maximize, let's say we want to f of x and y under the constraint, let's say, g of x and y, of course that would just be equal to constant, right? And if you wanted to, you could say that z equals that. If you wanted to minimize or maximize, I just said maximize, just slide something right up here, what would we have to do? Well, we could say that the gradient of 1, right, the normal vector to 1, would be equal to the gradient of the other. Well, basically saying what? The normal vector of 1 is the same as the normal vector of the other one, except for they could be different lengths. So one could be off by a constant multiple. And what we normally use here, this is what the actual Lagrange multiplier is. Normally we use something like a lambda here. Now I know it doesn't look like it when you just first look at this, but this is actually a system of equations because the gradient here, remember this is the vector f sub x, f sub y is equal to g sub x, g sub y. And we write one more step. Let's see, f sub x, f sub y is equal to lambda g sub x, lambda g sub y. Well, if two vectors are going to be equal to each other, then their components have to be equal. So f sub x has to be equal to lambda g sub x, and f sub y has to be equal to lambda g sub y. Okay, so what we end up with here is a system of equations. Now, how many variables do we have in here? Well, of course we have x's and y's, but we also have this new variable lambda, which means we have three equations. Three variables, which means we need three equations. Well, here we only have two from this, but we do have a third equation that we know has to be true. We know the constraint equation has to also be true, so we always get our last equations from that. So there we go. We ended up with a system of equations that we're going to have to solve. Now, remember, the only thing we're really looking for is the x and y values. Lambda is just telling us how much larger one normal vector is than the other one. So technically, we really don't care about the lambda. So we're going to go about and solve just for the x's and y's. All right, I'm back. Sorry for the cut. I had to go find an eraser. So let's see how we can actually apply the Lagrange multipliers. Well, let's do this first. Instead of taking a look at how the Lagrange multipliers work, let's take a look at how we optimize stuff back in, say, first semester calculus, just to get a reminder. So let's say that this is somewhat of a Calc 1 problem. Let's say we want an open top box to have a surface area of, let's say, 108. Oh, should I write the word of 108 square inches. What is the maximum volume of the box? Okay, so we want to make ourselves a box, an open top box, and I'm going to actually add one more kind of constraint to this here in a second. So there's our box, and an open top just means it doesn't have a top on it. Let's do one more thing, an open top box with a, let's make it a little bit easier on ourselves. And say that this thing has a square bottom, which means these two sides are the same. I don't know, let's call those x's, and let's call the height of this box y for some reason. All right, so we have two things we want to do. We want to minimize the volume, and we know that what we want for the surface area. So let's start with the volume, because that's going to be our primary equation, the one we want to minimize or maximize. Of course, it's just a box, so length times width times height. So that's going to be our x squared y. All right, so we also have a constraint here. So our constraint would be that the surface area, well, the surface area, we have 5 surfaces, one on the bottom, that's x squared, and 4 sides, and the area of each one of those sides is x times y. Now we know that we want this to be restricted to 108 square, square inches. So here we go, here we have our primary equation and our secondary equation. So using the same kind of notation I did before, this was kind of our f of x and y, and this is going to be our g of x and y. But how did we do this in Calc 1? Well, we knew we had to take the derivative of the volume, because that's what we were trying to minimize or maximize, but it had too many variables in it. So what we always did is we would take our constraint and solve for one of the variables. And here you can see that y is the easiest one to solve for. So 108 minus x squared, divide everything by 4x. So we get y is equal to, what's that going to reduce to? 7 over x minus x over 4. X over 4. Okay, that's what our y equals. So let's go ahead and plug that into the other equation. Now we'll get our primary equation down to one variable. So now I can say the volume, of according to this problem, is going to have to be x squared times 27 over x minus x over 4. All right, we can simplify this a bit. So our volume will be 27x minus x cubed over 4. All right, so to find a min or max in Calc 1, all we did is we took the derivative. So dv dx would be 27 minus 3/4 x squared. And we're going to want to know where that is equal to 0 or undefined. Well, that's a polynomial, so it's never undefined. So we would need to know when 27 minus 3/4 x squared is equal to 0. Well, moving the 27 over, we would get x squared is equal to 36, right? Multiply both sides by -4/3. And then, of course, take the square root of both sides. So the solution to this would be plus or minus 6. Now, in this case, though, x represents the side of a box, so it can't be negative. So just from the physical attributes of this property, we know x has to be equal to 6. Well, if we know x is equal to 6, we should be able to figure out what y is equal to. So y is equal to 27 over 6 minus 6 over 4. So if we reduce that, 3 goes into both of those, that's 9 halves minus 3 halves, 6 halves, so y is equal to 3. Okay, so not too bad of a problem. We now know the dimensions of our box. We go length, width, and height. That would be a 6 by 6 by 3 box, length by width by height. Now, that was all Calc 1. We didn't do anything new here that we haven't seen in the past. So I wanted to show you that this is still a viable method for finding maxes or mins of a constraint type problem. The only problem with our Calc 1 method is it can only handle one constraint, right? If we had another constraint, it would get too complicated for us to do with this method. That's why we need to find a newer method. So let's do the exact same problem. I'm not going to change anything. I'm just going to get all this out of here. Let's take a look at how Mr. Lagrange handled this problem. So by definition, this is what if we're going to keep with the same letters we did before. That's the function we want to minimize or maximize. And our g of x and y is just taking the constraint equation and moving everything to one side. So that's x squared plus 4xy minus 108. Okay, so according to Lagrange, he said del f equals lambda del g. So the gradient of f, the derivative of this with respect to x, will be 2xy. The gradient of that with respect to y, or the derivative of that with respect to y, will be x squared. So equal to lambda times del g. The derivative of that with respect to x will be 2x plus 4y. The derivative of that with respect to y will be 4x. Okay, so you can kind of see the equations that we're going to get out of this. We're going to have 2xy has to be equal to 2 lambda x, and then we get x squared has to be equal to, oh, I missed something. I'm going to write out like this. So it'll be 2 lambda x plus 4 lambda y. Sorry. And then the second one, we get x squared equals 4 lambda x. Now notice here we got two equations with 3 variables in it. We have x's, y's, and lambdas. So we need a third equation, and the third equation is the actual constraint equation itself. X squared plus 4xy is equal to 108. All right, let me go back over here. So what we end up with is this is our Calc 3 method. We end up with this system of equations to solve. Now, the good news, bad news here is after you solve this, this will always give you the answer. The bad news is this is generally a nonlinear system and isn't necessarily easy to solve. And there's no exact one way to do it. So you might have to go freshen up on how to solve this type of system. All right, so I'm going to cheat here a little bit and do some things that maybe aren't great. Let's take this one. This looks like the easiest equation to me. X squared equals 4 lambda x. You could here divide out by the x, but remember, anytime you divide by a variable, you want to be extremely careful because it could be 0. However, since x is the bottom or the length of the side of a box, we know x can't be 0. That wouldn't make any sense. So technically, I can divide out x because I know x is not 0. Now we get x is equal to 4 lambda, or lambda is equal to x over 4. Now notice I solved for lambda because remember, I don't actually care what lambda is, so I want to get rid of it as soon as possible if you can. So let's go ahead and get us some more room up here. Let's go down. Let's plug it into this one and see what happens, right? Because this one doesn't have any lambdas in it, so my only choice is to plug it up here. So I get 2xy is equal to 2 times lambda times x plus 4 times lambda times y. Let's see what this reduces to. So I get 2xy is equal to, that reduces, so that's 1/2 x squared plus xy. Ooh, pretty ugly. Let's see. I got this xy thing. Let's at least get those all to one side. If I move all the xy's to one side, I get xy is equal to 1/2 x squared. Now again, we have x's on both sides. I could divide that out if I wanted to. However, we can get there a little bit easier because the last equation I haven't used yet is this, and notice it has the variable xy in it. So I can just replace xy in this with something that only has x's. So this is one way that you can do it. So I'm going to take x squared plus 4xy is equal to 108, and I know xy, according to this, xy is equal to 1/2 x squared. So I get x squared plus 2x squared is equal to 108. 3x squared is 108. Divide both sides by 3, so we get x squared is equal to 3 goes in there 3 times, 18 6 times. All right, we take the square root of both sides, we get x is equal to plus or minus 6. Same reasoning as before, we have to throw away that negative value, so here we just get x is equal to 6. Now that we have a value for x, we got to plug it in somewhere that we have a y. So you can plug it into this equation, right? This one has a y in it. So if I plug it in there, I get 6x, I'm using this, xy is equal to 1/2 x squared. I get 6x is equal to 1/2 6 squared. So 6x is equal to 18. Oh, sorry, this is a y. Plug in for the x. So divide both sides by that, we get y is equal to 3. So we end up with the same exact answer, 6 by 6 by 3. Right, so you should be asking, well, this seemed a lot more complicated than the Calc 1 method. And I would agree in this case because, well, we're using a higher level method to solve a very simple problem. So yeah, it would get more complicated. But this one can handle a lot more real world problems. Generally when you're engineering or designing things in the real world, you have more than one constraint. So this type of problem can actually expand into 2 directions. Let me write it like this. Now, what do I mean by expand into 2 directions? Well, the problem that we just did, we really only had 2 independent variables. We had x's and y's, and I kind of did that to cheat, so we would only have 2, by making it a square bottom box. But what if the function that we're originally trying to minimize or maximize is a function of 3 variables, and our constraint g of x, y, and z has 3 variables? Well, the only difference that this happens is when you do the gradient, you get one more equation from the gradient. That takes care of the one more variable. So the equations that you would get from this, you'd have f sub x is equal to lambda del g, f sub y is equal to lambda, oh, let's do it, I'm writing it different on both sides. Let's do g sub x, g sub y, and f sub z would be equal to lambda g sub z. Of course, there's 3 equations with 4 variables, so our last one would actually be the constraint equation itself. And there's the 4 equations with 4 unknowns. So you can expand, this just expands perfectly for more independent variables. So the more independent variables you have, just means the gradient part gets bigger and bigger and bigger this way. However, so this is if you have more independent variables. If you have more constraints, let's go over here and just say, which is really more realistic in the real world to have a bunch of constraints. If you have more constraints, let's say that, again, we're going to start, let's just go back to 2 variables. So here's the thing that we want to minimize or maximize. Our z is equal to f of y, but our constraints are g of x and y is equal to some constant, h of x and y is equal to, I don't know, another constant. And you could keep going like this. Well, how does this expand? Well, the idea is the same. The gradient of each one of these has to match the curve at the same spot, so you'd end up with just a whole bunch of normal vectors with different lengths. So the gradient of f has to be equal to some multiplier times g plus also some multiplier times the other constraint function. Oh, gradient. There's my gradients. Gradient g plus mu gradient h. So we added what's called just another Lagrange multiplier. Mu is generally the second one we use. Again, I guess when he did this, these are the ones that he tended to use. So if you write this out, what you end up with for this case, since we have 2 variables, this would be f sub x is equal to lambda g sub x plus mu h sub x. F sub y is equal to lambda g sub y plus mu h sub y. Now notice here I have 2 equations, but I have 4 variables. I have x, y, lambdas, and mu's, so I need 2 more equations. Well, just like always, the last equations we get are always from the constraints. Now in this case, we have 2 constraint equations. So we have g of x and y has to be equal to c, and h of x and y has to be equal to, I don't know, some k. So notice here, there's our 5 equations. And because we have x, oh, I'm sorry, 4 equations. I went too high. There's our 4 equations, right? Because we have x, y, lambdas, and mu's. So we have to have, we have 4 variables, we need 4 equations. And this can keep expanding. No matter how many constraints that you have, you just keep adding on the gradient of each one of those constraints. And then all the extra equations are your constraint equations. Now, of course, the more complicated this gets, the harder it is to do by hand. But that's why we have computers out there to help us solve really, really complicated problems like this, or at least approximate the solutions to those types of problems. So this is a really great method. Make sure that if a test question or anything says use the Lagrange multipliers to minimize or maximize something, that you're not using the Calc 1 method, even though the Calc 1 method may work perfectly fine. If you're told to do Lagrange multipliers, make sure you're using this method.